All right, people, these are the solutions to TME plus work external equals TME at a different point. So question 14, you have a 2 kilogram block attached to a spring of force constant K equals 500 newtons per meter. Make sure you're comfortable with those units. It is pulled 5 centimeters or 0.05 meters to the right from equilibrium or unstretched. That sounds really fancy because vertical springs, equilibrium is complicated. Equilibrium for horizontal springs is just unstretched because that's when there's no net force. Okay, so we're going to do it first without friction and then with friction. So we are going from point A to point B, and we want to find the speed at point B. And okay, so sorry to think about what they mean by equilibrium for the second part. So no, but sorry. So we're going to say TME at A, I think I can do it up here, equals TME at B. We're doing A and there's no friction. Okay, so let's practice writing everything you might possibly have. Sorry, plus 1/2 mv squared. All of that at point A equals mgh plus 1/2 kx squared plus 1/2 mv squared at point B. Okay, so we pull it back at point A and we release from rest. So that means we can throw out the kinetic energy term. That's 0. Do I have spring stored energy? Absolutely. I don't know why I'm doing this backwards, but we have 1/2 500 times 0.05 squared. Do I have mgh? Well, let's decide that that's sea level. So no, I don't have that term either. So at point A, all of the energy is stored in the spring because I haven't gained height and I'm not moving. Okay. And then at point B, the spring is unstretched, right? You can see it's stressed here, storing the energy like the pole and the pole vault. Boom, not stressed anymore. So therefore, there's no more spring stored energy. And we're still at sea level. So all of the energy is now kinetic energy, and that's why we needed the mass. And so it goes from all spring to all kinetic. And I would like to calculate that number. So, all right, so we have 0.625 equals VB squared, or V at B is the square root of that, or 0.791 meters per second. Okay. Let me do. All right, people. The reason I was pausing a little bit through A is that I was jumping ahead to B, and I don't like the way they said find the speed as it passes through equilibrium, because technically this is no longer equilibrium if there's friction. So we're gonna do one. We're gonna do this problem where we're gonna look at equilibrium where there's a spring and friction. So I want to make this simpler. I'm going to pretend like this question says find the speed as it passes through unstretched, because that's what matches my answer key, and I want this to be a little bit easier. Okay, so we're going from point A to point B again, but this time there is energy loss. All right, so I'll give myself more room. So we're going to have TME at point A plus the sum of the work done by anything that will take energy away from the system or put energy into the system equals TME at point B. All right, TME at A hasn't changed. We already know what that is. That was 1/2 500 times 0.05 squared, or 0.625 joules. Like that hasn't changed. We pulled the spring back by the same amount, so it's still storing the same amount of energy. And we're still not moving, and we're at sea level. Okay. What's changed is that as the block goes from A to B, friction is acting opposite the velocity vector. So we're going to have plus FD cosine theta of friction equals TME at B. And again, at B, spring is done giving away energy, still at sea level, but I do have some speed at B, and then because of friction, it's going to be less than the number we had before. And so that is what we're looking for, 1/2 mv squared at B. Okay, so moving on, 0.625 joules plus force of friction. So I was telling somebody during office hours today, I highly recommend that you go off to your miscellaneous column to calculate friction, and I'll explain why. So friction is 0.35, and this is a boring problem, so the normal force is equal to the weight. So 0.35 times 2 kilograms times 9.8 is 6.86 newtons. Okay, so that is what friction is. D is the distance through which friction acts. That's why I showed you the Punkin' Chunkin' video, or why you want to have follow through when you play sports, is because the greater the distance through which the force acts, clearly the more effect it's going to have. So the distance is 0.05. Okay, and you got to do enough of these problems to know that, remember, I made a big deal about positive, negative. This is always positive in this formula. Positive, positive. This is magnitude, magnitude. The only minus sign you're going to get is from this cosine of theta. And this is also counterintuitive because most of the time we're going to look at the diagram, the picture, the original picture, to find theta. And there's no freaking theta in this picture. So you may want to draw yourself a picture saying friction is pointing to the right and my velocity vector is pointing to the left. The angle between these two is 180. So this is cosine of 180. And that's going to equal 1/2 m, which is 2 v at b squared. Okay, and we like that cos 180 because that's going to give us a nice clean -1. So we had 0.625 joules of energy. Friction took away 0.343 joules, and that is the square of my velocity. Oh, and then I forgot to finish my little hint. I would recommend that you do miscellaneous to get friction, just cleaner, because you can see there's a lot going on here. And I do these problems for a living, and I will put in the mu, I will put in the m and the g, and then I'll kind of go, oh, I already put in the 3 terms here. I will drop that distance d all the time. So please know that if that happens on a solutions, I apologize in advance. It's just really, really easy to do. Could just be something that I do, but watch out for that. It's just really easy to drop that distance term. Okay, when you solve that for velocity at B, you get 0.531 meters per second, which is less than what we had before, of 0.79. Okay, so again, I might go on to the book solutions. Just pretend like this question said unstretched. And we'll see later on what equilibrium means for springs with friction. Okay, so that is question 14, with and without friction. All right, people, this is question 15, and it, I think, looks deceptively more simple than it is. There's a lot of little easy ways to go wrong here, so Please make sure that you practice this incline type question. Okay, so we have a crate of mass 10. We need the mass for the kinetic energy being pulled up a rough incline. So that means we have friction with a force of 100 newtons. And for some reason, again, I got this from a book, for some reason it has speed at A, and I almost got rid of that. And I'm like, no, it's good for people to know things don't always start at rest. So it has speed at A, and we want to know the speed at point B. So I initially I know this is a bit confusing. This represents the initial speed. And again, I don't know how the block is moved. Well, maybe it's moving. I don't know. It doesn't matter. It's a fake physics problem. It's already moving and somebody pushes it, continues to push it up the ramp at constant speed. So we are clearly going from point A to point B. So we're going to start with all of the energy at A plus the sum of everything that's happening to it equals all of the energy at point B. So there's no springs in this system, so there's enough going on that I'm just going to go ahead and not include that term as a potential term. It's fine if you want to keep doing that to get in the habit, but there's no spring. So we're just dealing with gravity and kinetic energy like when we did the pendulum lab. Okay, what's tricky here is that you have, this person is clearly an outside force. So we have FD cosine theta for the work done by the person or whatever is causing that. But you also have friction. So we also have to include the work done by friction, right? So if your Venmo account, you can have money coming in and money going out. We need to account for all of it. Don't assume that this is always going to be just a single force. We have two external forces here. Okay, and then at point B, I'm above sea level. I'm going to have some height, and I'm moving because that's what it's asking us to find. Okay, that's the big picture. Okay, I have some energy, friction, or the person put some more in, friction takes some away, and then I have different amount of energy. Okay, and you can see the mass doesn't cancel because it's not hidden in that F term. Okay, so MGH, let's call this sea level so we can get rid of that. But it is moving. So we have 1/2 10 times 1.5 squared. All right. You all are good at force diagrams, so take the time to draw the force diagram and think about it, because I can't tell you how many times on a test people were like, oh, cos theta, I need a theta. It's right there. That's not the theta we're talking about. Force is 100 newtons. The distance is this 5. It is the distance through which the force acts. So in a minute, I'm gonna give you the height here is 1.71 meters. Height at point B. Sometimes I put all those values on the test picture so that you're not wasting time doing trig identities. I'm not going to tell you on the test, oh, that distance is the 1.71 or that distance is the 5. You need to understand conceptually, this 5 is the distance through which the force worked. The bigger that distance, the more work it did. Okay, this 1.71 is related to the 5, but it did not, what's important is that force traveled through that 5 meters, not the 1.71. Okay, the other thing that's important is, let's see, pink vector is your force vector, blue vector is your velocity vector. The angle between these two vectors is 0. They're pointing in the same direction, so there is no difference between them. So that is the work done by the person. That makes sense. 500 joules, they put energy into the system. Okay, so now let's think about friction. I highly recommend, let's go off into the miscellaneous column and let's calculate that force of friction. We have mu, that's pretty straightforward. The normal force on an incline, remember, it is not balancing all of the weight. The goofy mnemonic that you can just go straight to is mg cos is the part that makes contact or crushes the incline and causes the normal. Okay, so this is 0.4 times 10 times 9.8. This is 20 degrees. That's why they gave you that. Okay, and then you find a friction of 36.84 newtons. Again, lots of stuff going on. I would do that somewhere else so that you can keep your work clean and not make a mistake. That's friction. Friction also, clearly it's important that it's 5 meters, right? The longer this distance here, the more nooks and crannies the box bumped into, the more work that was taken away, the more energy was taken away. So friction, 5 meters, this is positive, this is positive. The only place you're going to get a negative sign is from this cosine theta. So friction is down the incline and the motion is, I was making that blue, the motion is up the incline. The angle between these two is 180. So that's cosine of 180. Okay. So lots of stuff going on, which is again why it's helpful to have friction off to the side. At point B, we are above sea level. So you have plus M, which is 10, G, which is 9.8. This 1.71 came from, instead of breaking down a force vector, it came from saying, you know what, this 5 is my hypotenuse. So 5 sine of 20 is 1.71. So that's the height at point B. So some of that energy went into giving the block some height and leaving a little bit less for the kinetic energy. All right, so that is the physics part. And again, where people really get stuck is in this cosine theta stuff. So make sure you understand what the cosine means at every point. Okay, and then just for curiosity's sakes, the box had 11.25 joules. The person, whatever that is, put in 500 more joules, but friction took away 184 joules and turned it into heat. And then the box had 168 joules of stored energy because it was above sea level, and whatever's left over is kinetic. Kinetic energy gets the dregs. Okay, so if you add up all of this, you get at the top, at point B, it has 327 joules. 168 of those joules are gravitational stored energy. The remainder is kinetic. Solving that for VB, you get the square root of 31.85 or 5.64 meters per second. Whew. All right, so in this case, a lot simpler to, probably you were thinking to use sigma F equals ma, right, to do an incline problem. But it's super important that we understand the concept of energy and what's bringing energy in and what's bringing energy out. All right, so that is question 15. Okay, we have a sled given a kick on a frozen pond. It's got an initial speed, and then there's friction, and then it comes to rest at point B. And we're looking for the distance this sled travels as it comes to rest. All right, so we're going from A to B. Clearly there's energy loss because there's friction, so we're going to have TME at A plus the sum of all the work done that is putting energy in or taking it away equals the TME at B. No springs, so, and this is sea level, so there's no MGH, there's no spring stored energy. So at point A, it's all kinetic energy. Friction is doing work on it. That's our distance D. That's how we're going to figure that out. And at point B, It's at sea level. There's no spring. It's not moving. It doesn't have any energy left. Friction took away all of the energy. So what happens every time you brake your car. Brake, B-R-E-K, brake. Um, and so let's just plug in the number. So you have 1/2 40 times 2 squared plus friction. So let's go over to our miscellaneous and say friction equals mu n. Mu is 0.1. This is a boring problem. The original problem actually didn't have the mass in it because the mass is going to cancel here. It isn't every term. But I think it's good to get used to thinking about what the joules are. How much calculating the actual energy. But you could have done this out in variables and then canceled the mass. Oops, sorry, newtons. I was talking about joules, so I wrote joules. Okay, so friction is 39.2 newtons. The distance it traveled is what we're looking for. And friction is opposite the velocity. And the velocity is this way. The angle between these two vectors is 180. Okay, so this is clearly 80 joules because we had 80 joules minus 39.2 D. So because this turns into just -1 equals 0. So 80 equals 39.2 D. Divide both sides by 39.2. And you get that the sled travels a distance of 2.041 meters. All right, you could have done this problem using sigma F equals ma and then don't know, don't care. And if you, I don't want to waste too much time or use up too much time, but hidden in this delta KE is don't know, don't care, right? That's why we got like V squared minus V naught squared. That's difference in kinetic energy with the mass canceling. So you could, again, if it's in a situation where you can't check your work online or whatever, you could check your work to make sure you didn't make any mistakes using the old school sigma F equals ma, and then you don't know, don't care. All right. I like that question, even though it's in some levels basic, because it's classic to say, I end up with no energy. And sometimes that seems a little bit weird. So I wanted people to have practice with that. Okay, and then 22, I chose this question because each force acts for a different amount. And I want to explain to you that, so let's quickly look at the problem. You can read it yourself. But so the skydiver jumps out of the airplane from rest at a certain height. They fall for some distance that the problem doesn't tell you directly. And with the chute closed, they're still going to hit some air molecules, right? So they're colliding with air molecules and they are experiencing 50 newtons of air resistance. When they open up the chute, they're going to trap more air molecule. They're going to literally run into more air molecules, and that increases the force to 3,600 newtons. All right, so we have C. When I put questions like this on the test, sometimes people feel like they have to go from A to B and then from B to C, and that's not wrong, but it, potentially could cause you more time than you want. So we're going to go TME at A plus all of the work that happened to it equals TME at C. All right, we have to set sea level, and unlike vertical springs, this is going to make sense. Let's just set the ground to sea level. Nice, easy to think about. Okay, so at point A, there's no springs in the problem and they're not moving, so they only have MGH at A. What is tricky is that we have the work done by the parachute from A to B plus the work done by the parachute from B to C equals, at C, they're at sea level, yuck, 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 That was unintentional. So they only have kinetic energy at C. Okay, but the trick is you're going to have two different work terms with different distances. That's fine. You're just calculating it. Okay, and the other thing that's a little bit tricky is figuring out what these distances are, but it's not hard. You just got to pay attention. Okay. The mass of the person is 80 times 9.8 times 1,000 meters. Okay, and then we're going to do plus the work done from A to B. So FD cosine theta 1 and I didn't plus FD cosine theta 2 equals 1/2 mv squared. So 1/2 80 times what we're looking for squared. Okay. I want to get this as a number. Hold on. Okay, that person had a whopping 784,000 joules of energy just from being up there, like they're not even moving yet. Okay, and then that air resistance, the air molecules have a force of 50 newtons. And then the distance they worked in the period 1 was 800 meters, the difference between those two. And then the person is going down, but the force is up. And the angle between the force and the motion is 180. Okay, so that is the work done from A to B. And then from B to C, the force jumps up to 3,600 newtons. The distance is 200 meters. But again, the force is up and the motion is down. So that's another cosine 180, which is what you want, right? You want the parachute taking energy away. Equals 80 over 2 times v squared is 40v squared. Okay, so while you were gone, trying to think where I left off. I ran these numbers. So in the first period, air resistance took away 40,000 joules. In the second period, it took away 720,000 joules. So even though the distance was shorter, the force was so much bigger. It took away more energy in the second section. And so right before they hit the ground, they still had 240,000 joules of energy. Setting that equal to kinetic energy gives you a speed of 24.5 meters per second. That's about 50 miles an hour. That does not seem safe to me. There was a part B to the question that was like, how much sooner should they have opened the chute in order to have a smaller speed? Yeah, okay, so that is question B. So we'll do that in a second because 50 miles an hour, that's a lot. Okay, so remember some of the numbers you have, hopefully you're taking good notes. And we're going to do B, but some of the things are going to be really, really similar for B. Okay, so there's a little bit of algebra here. So what is tricky is the way the question was worded was that at what height should the parachute be opened? So what they're looking for is H. They could have said, after falling, what distance should the parachute be open? And then you'd be looking for D. But they said, what is H? And again, if you misunderstood that on a test and you found D instead of H, not a big deal. You're still doing the same problem. You just, misunderstood which dimension I wanted you to solve for. So, but this question says, at what altitude do they open the chute? And so I'm calling that altitude H. So instead of being 200, that altitude is H. So if that altitude is H and this whole thing is 1,000, then this distance here is 1,000 minus H. And that's, once you've done the first part of the question, that's 90% of solving the problem is understanding how to write these distances algebraically. Okay, so when they jump out of the airplane, they still have 784,000 joules. That hasn't changed. So don't make more work for yourself. That is the same value as before. But the work done by the chute in the first period is still 50 newtons, but the distance is 100 minus h. And then this is a little confusing. I ran out of room. And then the work done by the parachute in the second time interval was 3,600 times h. Both of them have a cos 180 still. Same reason as before, so I won't go over that again. Right before it lands, we're told that we want the person to have a speed of 5 so that they can land safely. That's about 10 miles an hour. So we want there to be only 1,000 joules left over. So that's what we know this time. What we don't know is h. So there's a little bit of algebra. The 784 comes straight down, but you have 50 times 100 times cos 180, which is how you get minus 50,000. And then you have 50 times minus h times a negative 1, so that becomes positive. And then you have 3,600 h times cos 180, which is negative. So I'm sorry, this is all one line. So you have initial energy and this other kind of algebraic stuff that came from this algebraic stuff. And that reduces to minus 3,550h equals minus 733,000. So it's good that we got two minus signs because we want that h to be positive, and you get h equals 206.5 meters, which I thought was fascinating. I didn't write this question. The textbook authors, not that much different, right? It was 200 meters. So 6.5 meters, that's about an atrium and a half. Opening up the chute that much sooner made a big difference in hitting the ground safely. Okay, so that was a lot, but good practice with, when the distance what you don't know is the distance, which we also saw in the sled question, right? So you want to be flexible so that you can solve for lots and lots of different things. All right, this is a long problem set, but it's all good stuff. Okay, so we have a toy cannon. You have done this first part of this problem, well, a different part of this problem already. So this problem might look familiar, but this is slightly different questions. Okay, so we have a toy cannon, blah, blah, blah. You've done this question already. Question A, determine the location at which the spring force equals the force of friction. So you did this problem before where you just found the speed at B. That was in a different problem set. And there was friction before. So the spring is pushing out with a force K delta X. Delta X is decreasing. So the spring force is getting smaller and smaller and smaller because it's getting closer to unstretched. Friction is a constant force of, they calculated it for you, of 0.032 newtons. So K delta X starts out at, doesn't really matter, something bigger than 0.032 newtons. But it's going to go from some big force, and I don't remember what it is, to 0. So at some point, it's going to be 0.032 newtons. So the question is asking you to find when these two forces are equal. So we're going to say the sum of the forces are 0. K delta X is positive minus the force of friction, and they are balanced. All right, and then the spring constant is 8. I'm going to keep using the units because people are having trouble remembering those. Times 0.05. Bring that over to the other side, equals 0.032. Oh, my bad. We're looking for delta X. And so delta X is 0.032 4 newtons over 8 newtons per meter, and you can see that the newtons cancel and you get 0.004 meters. So 4 millimeters, not very stretched. So somewhere here, whatever to scale, the two forces are equal to each other. Okay, that's a 0. That's not an 8. So 0.04 meters is the answer to question. It says A here. It's B in the PDF because there was a previous question you did. All right. Okay, so we found where the spring is pushing to the right as much as friction is pushing to the left. Now we want to find the speed of the ball as it passes through the equilibrium position found above. This is the maximum speed of the ball, which is why I wasn't sure that very, very first question in this problem set wanted you to find the speed at equilibrium, which is what we're doing now, or unstretched, which is what I decided that other problem was. Okay, so now we're going from A to this B. This was from previous. So we're going to say TME at A plus the work done by friction equals TME at B, which is equilibrium. So if you want to call that E, that works for me. Okay, so at point A, we are at sea level, so we don't have MGH. We have spring stored energy. We are not moving. So it's just all spring stored energy plus the work done by friction equals, and this is tricky. This is what people get wrong on the test. People get all focused on finding the speed that they forget that at B, we're not doing unstretched. We are doing, the spring is not at the dash line. So the spring still has energy. And we are looking for the speed. So 1/2 kx squared is 1/2 8 times 0.05 squared. They gave you friction. We don't have to go to miscellaneous column to find it. That's friction. The distance it traveled, this is tricky. It started at 0.05. It started kind of at negative 0.05 and it ended at 0.04. So it 0.004 is what I have. Let me check my keys. Okay, sorry about that. The point B was 0.004. I hope I did that right in the first part, but that distance here is 0.004. So I can't do this in my head. Take the time to really figure out what's going on. I know it may not feel interesting thinking to you, but it's important detail. So this distance is 0.05. This, I have trouble writing 4s with my tablet. The point A is the spring is stretched by 0.05. Point B, the spring is stretched by 0.004. So clearly not to scale, that's much smaller. So we need to find this green distance, which is the difference, just like with the parachute question. If this is 0.05, that's 0.004, then that green distance is 0.046. So that's the distance that friction acted from A to B. All right, so the distance, like the diagrams are super important here in some of these problems. We're not trying to trick you. It's just that's what you know. Like that's how you would describe it to somebody, which isn't always the way that it's, going to make it the distances you need, right? Sometimes you have to do some extra work. Okay, so going back to what we had so far, we had spring stored energy plus the force of friction, and then we needed the distance through which friction acted, and that is 0.046. Because we didn't make it all the way back to the dash line. We were 0.004 meters shy of the dash line, if that makes more sense to you. So we're 0.04 meters shy from returning from 0.05. So what's left is we went 0.046. Okay, and then, so we got the distance. Friction is cosine of 180 because it's opposite the motion. And that is all on our left-hand side, and that is equal to 1/2 K, which is 8, times this tiny, tiny 0.04 squared, plus 1/2 M, which is also tiny, tiny, because it's in grams, times V at that point squared. Okay, that's a lot. But hopefully you're following through and listening to like what these numbers mean. Okay, so I will work out what the numbers are. Whew, okay, I apologize in advance. Some of these numbers are annoyingly small. Um, so because it's a toy. So it started out with a hundredth of a joule, right? So it's got 0.01 joules of energy. Friction took away a tiny amount. And then at point B, it still got spring stored energy. Not very much, but and so you might get the right answer. Neglecting this, you might get pretty close to the right answer, but I will still take a point on the test because you're missing the point that it does have some spring stored energy. Okay, and then whatever's left over is kinetic energy. So I wanted to see what happened here. This minus that, again, tiny, tiny amount of energy. Tiny, tiny. When it came out, though, V squared was 3.19. Take this square root, and so the speed is 1.79 meters per second. So, because the object itself had so little inertia that wasn't like we still ended up with something significant. And let's see, and the speed at B was 1.4, so we're good-ish. I mean, I'm saying we're good. I just don't know. That does not definitive to make sure that you're right. But it has a speed of 1.8 at point B. It's going to continue to slow down even though the spring is pushing it because friction's taking away energy faster than the spring is putting it in. And then it's all downhill from there. Then from C, from B to C, it's slowing down. And then from C to, let's call this D now, it's spring's gone. And so friction is only taking energy away. And at that point, I referenced the previous problem you did, and you got a speed of 1.4. So I'm just saying that seems reasonable. Okay. So just quickly, before we do the very last question, the moral of the story is maximum speed occurs at equilibrium. All right. And so set the two forces equal. And because we're not at unstretched, we're going to have spring stored energy. All right, and I'm not sure why this is 55, because I actually don't think this one is as tricky as some of the other ones we have tackled. But let's just go ahead and do this, and then we are done. So we have point A, we have point B. You could find the speed at B, but we don't need to. We could find the speed at C, but we don't need to. What do we care about? Let's see. Oh, maybe we can't find the speed at C because we don't know what friction is. So, okay. It compresses the spring 0.3 meters from its, see, they're calling it equilibrium, and maybe they should call it unstretched. Okay, so that's where the spring wants to be. Point D is 0.3 meters. So that's where the block comes to rest. So this is point D. And the spring is compressed by that amount. So at A, it has some energy, friction takes some away, and then compresses the spring. Okay, so we have, do we have enough room here? Okay, so we have TME at A. I'll move back up so we can see what's going on. TME at A plus the sum of everything that happened to it on the way to D. All right, so we got to set sea level. Let's call it that, sea level. So we have MGH at A. I'm above sea level. Spring doesn't have any energy, not moving, so it's all MGH at A. All right, nothing happening here. Oh, we have work done by friction here. On the test, I could throw in a fan cart somewhere. The fan could turn on and off for some random amount of distance to just pay attention. Think about forces. Y'all are good at forces. And then at point, we could find the speed just before it impacts the spring. We don't care. We just want to know, what are we looking for? Oh, we want to know mu or something. Yeah. At D, it's not moving. It's at sea level. So that term 0, it's not moving. All of the energy is in 1/2 kx squared. Okay, mass does not cancel. So let's plug things in. It's 10 kilograms, 9.8. The height is 3. Plus friction is mu times the normal. We're looking for mu, so not going to help to go do miscellaneous because we don't know it. Friction acts through 6 meters, but whatever friction is, it is opposite the velocity. That's 180. And 0, 0, 1/2 k is 2250. That's a massive spring. Yep. Times the distance 0.3 squared. Okay, so running through the numbers, this is 294 joules plus mu. It is a boring problem. The normal is the weight. So that's 10 times 9.8 or 98 newtons. Don't drop that 6 meters. I do it all the time. Cosine of 180 is a -1 equals 101.25 joules that ends up in the spring. Okay, and that makes sense because 101 is less than 294 because friction took some of that away. So this reduces to minus mu, there's your minus sign, times all of this is 588. And 101 minus 294 is apparently minus 192.75. Divide both sides by -588, and you get a mu of 0.328, and it is dimensionless. Check. Massively long problem set is done. In 2025, if you are still wanting more practice with TME plus work equals TME, I found some online questions, so those are linked at the top of the syllabus, and I'll try to put them in the review assignment, getting ready for the test. Okay, hope that is all good. Please reach out if you have questions, and thanks for listening.